Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
For decades, whenever we looked up at the night sky and just sort of imagined the future, the picture was always incredibly romantic, like almost cinematic.
Oh, absolutely. Very sweeping and grand.
Exactly. We pictured these sprawling lunar colonies with massive glass domes and giant gleaming industrial stations orbiting the gas giants.
Right, the classic sci-fi covers.
Yeah, and we'd imagine these bustling interplanetary trade routes, with freighters hauling cargo past the rings of Saturn. And right in the middle of all that science fiction were the asteroids.
The floating gold mines.
Right. We imagine them as these silent, drifting treasure vaults just floating through the dark, packed with unimaginable quantities of metals, water, rare materials, all just waiting to be cracked open by some future civilization.
It was a beautiful dream. A very compelling one.
It really was. But what is completely mind-blowing to me is that in just the last few years, that dream has actually crossed over.
It has. It really has.
It has shifted from speculative fantasy into a very serious, very intense realm of scientific research and economic planning and, frankly, intense geopolitical competition.
It absolutely has, though I will say the transition hasn't been as smooth or as cinematic as the science fiction authors promised us.
Fair enough. It rarely is.
Right. The reason for that shift is basically a sudden collective realization of scale. When you actually run the numbers on what is floating out there, the solar system contains resources on a scale that completely dwarfs Earth capacity.
It's hard to even wrap your head around, honestly.
It really is. And we are not just talking about a few interesting rocks scattered randomly through the void, which I think is a super common misconception.
Yeah, like you just grab a net and catch a shiny rock.
Exactly. We are actually talking about the foundation for an entirely new era of human civilization.
Wow.
The overarching reality here is that if we want to expand permanently into space, if we want to become a truly multiplanetary species, we cannot keep dragging every single piece of steel up from Earth.
Or every drop of water.
Right. Every breath of oxygen, dragging it all up from the bottom of Earth's gravity well. Those drifting vaults you mentioned, they aren't just a bonus.
They're a necessity.
They are the mandatory, permanent foundation for humanity's extraterrestrial industrial economy. Because without them, honestly, we're grounded.
Okay, let's unpack this, because the mission of our conversation today is to figure out how harvesting these ancient floating treasure vaults isn't just about some modern-day gold rush.
Oh, not at all.
It's not about bringing giant chunks of gold or platinum back to Earth to make a few massive corporations incredibly rich.
Which is what everyone assumes.
Right. But it is about something much, much bigger. It's about laying the groundwork for a self-sustaining ecosystem off-world.
Precisely.
But, before we can even begin to build an economy in space, we really have to understand exactly what is floating out there waiting to be claimed.
We do. We have to look at the geology.
Right. Think about the device you're listening to this on right now. The rare earth elements inside it required moving literal mountains of dirt to extract here on Earth.
Tons and tons of rock for just a few grams of material.
Exactly. Now imagine sourcing those elements not by tearing up a rainforest, but by catching a rock that has been drifting in the dark for 4 billion years.
It's a profound shift. But to do that, we have to completely rethink our understanding of what an asteroid actually is. Because they are not all created equal.
Right. They're not just giant uniform boulders.
No, not at all. They are incredibly diverse, and their chemical and geological composition basically dictates their value.
So how do we break them down?
Well, from an extraction standpoint, you can broadly categorize them into 3 major types. First, you have your C-type asteroids, which are carbonaceous.
Carbonaceous, okay.
Yeah, they're ancient, dark, and they often contain a lot of water-bearing minerals and organic compounds. Then you have S-type asteroids.
And the S stands for silicate.
Silicate, exactly. Primarily silicate rock mixed with the metals. This is closer to what you might imagine if you just pictured a standard rock in space.
Got it. So C-type and S-type. And
Finally, you have the M-type asteroids.
And the M stands for metallic.
You got it.
And from everything I'm reading, these are the ones where the sheer mind-boggling scale of the resources really comes into focus.
Oh, absolutely.
These are the ones packed with iron, nickel, cobalt, platinum, and rare earth elements. But here's what I don't get.
Okay, what's that?
If you look at Earth's geology, all the incredibly dense, heavy stuff, like the massive concentrations of heavy and precious metals, it all sank down.
Right. Down to the planetary core.
Yeah, it sank all the way down while the Earth was still a molten ball of magma. That's why it's completely inaccessible to us today.
We're just scratching the crust.
Exactly.
Yeah.
So if heavy metals naturally sink to the center of a planet during formation, how on Earth are we finding them just floating completely exposed on the surface of an asteroid?
That is the multi-trillion-dollar question. And the answer involves a level of violence that is honestly hard to comprehend.
Violence.
Yeah. What's fascinating here is that these M-type asteroids aren't just random clumps of metal that happen to stick together in a vacuum.
Okay.
Many of them are actually the exposed planetary cores of ancient protoplanets.
Wait, really? Exposed planetary cores?
Yes. You have to imagine the early solar system, around 4.5 billion years ago. It wasn't this orderly clockwork of orbits we see today.
Right, it was much messier.
It was a chaotic, violent pinball machine of celestial bodies. You had these early planets forming, sweeping up mass, heating up, and differentiating.
Differentiating, that's the process where the heavy stuff sinks, right?
Exactly. Differentiation is that exact process you mentioned. The entire body becomes molten, the heavy metals sink to the center to form a dense core, and the lighter silicates float to the top to form a crust and a mantle.
Wait, I think I see where this is going. So if a protoplanet successfully differentiates, it has a dense metallic core, a rocky mantle, and a crust.
It's exactly right.
It's basically a cosmic egg.
I like that. Yes, a cosmic egg.
But if these M-type asteroids are practically pure metal, that means something had to crack the egg.
A lot of things cracked a lot of eggs.
Oh, wow.
Yeah. During a period astronomers call the late heavy bombardment, these nascent worlds were just slamming into each other at tens of thousands of miles per hour.
It's just total chaos.
Total chaos. When a differentiated protoplanet suffered a catastrophic collision with another massive body, the impact would literally shatter the world.
Shatter an entire planet.
Yes. The lighter crust and mantle, the eggshell, and the egg white in your analogy were blasted away, completely vaporized or just scattered across the solar system.
And all that was left behind was the yolk.
The yolk. The dense, incredibly concentrated metallic core of a dead, shattered world just drifting there, perfectly exposed.
I mean, that is wildly macabre and amazing. We are literally looking at the guts of murdered planets.
It is a profound way to look at it, yeah. And those violent cosmic collisions did the hardest part of the mining for us.
They dug out the core.
They stripped away thousands of miles of rock to expose the dense interior. They created resource concentrations in these metallic remnants that are simply impossible to find on Earth's surface today.
Because on Earth, we'd have to drill to the center of the planet.
Which we can't do. Geologic processes over billions of years have either buried these materials deep near the core or they've been dispersed so thinly across the crust through volcanic activity.
Right, so you have to move mountains of dirt just to extract a few ounces of cobalt or neodymium.
Exactly. But out there, the concentration is practically pure. We are talking about a single, large M-type asteroid, theoretically containing trillions of dollars worth of raw materials.
Trillions, with a T.
With a T. Some of them might hold more platinum group metals than have ever been mined throughout the entirety of human history combined.
It's almost hard to wrap your head around those numbers.
Yeah.
But, you know, it's not just about what they're made of. It's about where they are.
Ah, yes. The geography of space.
Yeah, because when people hear the word asteroid, they almost universally think of the asteroid belt, right? Way out there between Mars and Jupiter.
Right. They picture Han Solo dodging rocks in the Millennium Falcon.
Exactly. Millions of objects, but incredibly far away.
Which, by the way, is largely a Hollywood fabrication anyway. The asteroid belt is actually incredibly sparse.
Wait, really? It's not a giant hazard course?
Not at all. If you stood on one asteroid in the main belt, you likely wouldn't even be able to see the next nearest one without a telescope.
Oh, wow. I had no idea.
But you're touching on a crucial point about logistics. From an economic and engineering standpoint, the main asteroid belt is actually a secondary, perhaps even tertiary target.
So where are we looking then?
The primary targets right now are the near-Earth objects, or NEOs.
Okay, near-Earth objects.
Yeah. These are asteroids whose orbits have been perturbed over millions of years, bringing them relatively close to Earth's orbital path.
And I guess that proximity makes them easier to get to.
It does, but it's not just distance. The geography of these targets changes everything regarding the energy economics of reaching them.
The energy economics. Okay, this completely blew my mind when I realized it because it feels so counterintuitive.
How so?
Well, you would naturally think that getting to the moon is always the easiest, cheapest thing we can do in space, right? Because it's right there in our backyard.
Right, it dominates the night sky.
Exactly. But because of orbital mechanics, there are actually certain near-Earth asteroids that require less energy to rendezvous with than the surface of our own moon.
It is wild, isn't it?
It's insane. How is that even possible?
Well, it comes down to understanding gravity wells and delta V.
Delta V.
Yeah, delta V is the aerospace term for the change in velocity required to perform a maneuver. It's essentially a measure of how much energy and therefore how much fuel you need to get from point A to point B.
Okay, so more fuel means a higher delta V requirement.
Exactly. Now, the moon might be geographically close, roughly 240,000 miles away, but it has a significant gravity well.
Right, it has enough gravity to pull the tides on Earth.
Exactly. So to land on the moon, you have to expend a massive amount of fuel to slow your spacecraft down and counteract that gravity so you don't just smash into the lunar regolith.
That makes sense. You have to brake.
Right. And if you want to bring anything back, you have to expend massive amounts of energy to take off again, fighting that same gravity to achieve lunar escape velocity.
But a small near-Earth asteroid doesn't have that problem.
Barely any at all. I mean, a rock that is a few hundred meters across has practically zero gravity.
So you don't really land on it.
No, you don't land on it so much as you gently dock with it. You just match its orbit and pull up alongside it.
Like two ships on the ocean?
Sort of, yeah. You don't need huge thrusters to brake, and you certainly don't need a massive launch vehicle to leave. You just give a little push, and you're on your way home.
Wow.
So the delta V requirement to rendezvous with specific NEOs and return material to Earth orbit is actually lower than the round trip to the lunar surface.
That's incredible.
It is. This is why these bodies have become the absolute vanguard, the primary targets for future mining missions.
Okay, so we have these exposed cosmic yolks packed with trillions of dollars in platinum, floating closer than the moon in terms of the energy required to reach them.
That's the setup, yes.
It sounds like the ultimate gold rush. You send a ship, you grab a mountain of platinum, you bring it home, and you are the richest person in human history.
Well,
But wait. I want to challenge this entire premise.
please do.
If I'm an investor backing a space startup and I look at the actual physics and economics of this, is all this talk about trillion-dollar platinum asteroids just a massive distraction?
The distraction from what?
From the water. If I'm an investor, you're telling me the real gold rush is actually for ice?
I am. Honestly, yes.
Wait, really? Ice?
Yes. If we connect this to the bigger picture, the entire economic model of space extraction requires a massive paradigm shift.
Okay, walk me through that.
The immediate ultimate prize in the solar system right now isn't metal. It is water. And to understand why, you have to understand the tyranny of the rocket equation and the gravity well we're currently sitting at the bottom of.
The gravity well, the invisible dictator holding all of human potential down.
It truly is a tyrant. I mean, right now, launching materials from Earth is crushingly expensive.
Because everything is so heavy.
Exactly. Every single kilogram of mass, whether it's a structural beam for a habitat, a tank of breathable oxygen, or a human being must overcome the massive gravitational pull of an entire planet.
Right.
This requires the Tsiolkovsky rocket equation, which essentially states that to lift a payload, you need fuel.
Makes sense.
But fuel has mass. So to lift the fuel, you need more fuel. And to lift that fuel, you need even more fuel.
It's just a vicious cycle.
A completely vicious cycle. Modern rockets are roughly 85 to 90% propellant by mass. They're mostly just giant, highly explosive fuel tanks required to lift their own fuel.
Leaving, like, what, 10% for the actual stuff we want in space?
If we're lucky.
Yeah.
Leaving only a tiny fraction of the rocket's weight for the actual cargo.
Yeah.
It is an incredibly inefficient way to build infrastructure.
Which means returning massive amounts of metal to Earth might actually be a terrible business plan.
It would be an economic catastrophe.
Really? A catastrophe?
Oh, absolutely. Let's run the thought experiment.
Yeah.
Let's say you do go out, you capture $1 trillion worth of platinum, and at enormous expense and engineering risk, you bring it safely down through Earth's atmosphere.
Okay, without vaporizing it or, causing a dinosaur-level kinetic bombardment event.
Right, assuming you land it safely. What happens to the global platinum market the second that cargo touches the ground?
Oh, the supply shock.
Exactly.
The sudden massive influx of supply would instantly crash global commodity prices. I mean, platinum is valuable because it's rare on Earth's crust.
Exactly the problem.
If you suddenly dump thousands of tons of it onto the market, it's not rare anymore.
The price per ounce plummets. That supposed trillion-dollar asteroid is suddenly worth a fraction of that, but your mission costs the research, the rockets, the orbital maneuvers. Those costs remained astronomical.
So you've effectively bankrupted yourself by succeeding too well.
Yes, the ultimate Pyrrhic victory. You bring home the gold, and the gold turns to lead.
Man, that's a brutal reality check for the space gold rush.
It is. The true value of asteroid mining, the paradigm shift we need to make, is keeping the resources in space.
Not bringing them back.
Right. And that is where water becomes the most valuable commodity in the solar system. You mentioned earlier that the C-type asteroids are carbonaceous and often contain water-bearing minerals.
Yeah, the ancient dark ones.
Exactly. That water is the key to unlocking the entire solar system. I mean, water is life support for astronauts. It provides hydration and breathable oxygen.
Right, the basics.
It is also excellent radiation shielding. A thick jacket of water around an orbital habitat blocks high-energy cosmic rays brilliantly, much better than heavy metals do.
I hadn't even thought of that. Water is a shield.
It's fantastic for it. But most importantly, water is fuel.
Because of electrolysis.
Yes.
I mean, we all know water is H2O.
Yeah.
If you capture ice from a C-type asteroid, melt it, and run a strong electric current through it, presumably powered by what? Massive thin film solar arrays or a nuclear microreactor?
Either one, yes.
You split the molecules, you separate the hydrogen from the oxygen, and suddenly, sitting out there in the vacuum of space, you have the two exact ingredients you need for high-efficiency rocket propellant.
Liquid hydrogen and liquid oxygen. Hydrolox.
Hydrolox.
It's the exact same propellant mixture that powered the space shuttle main engines. By processing water from an asteroid, you have just created an interplanetary gas station.
Wow, an off-world gas station.
And this fundamentally changes everything about deep space payload capacities. Think about how we do deep space missions right now.
Okay.
If a spacecraft wants to go to Mars or Jupiter, it has to launch from Earth, carrying every single drop of fuel it will need for the entire journey, including the deceleration at the destination.
Because there's nowhere to stop along the way.
Exactly. That severely limits how much scientific equipment, shielding, or cargo it can carry. Because, again, the rocket equation dictates that most of the mass must be fuel just to escape Earth.
Right.
But if you have water-rich C-type asteroids acting as refueling depots in high Earth orbit or at Lagrange points, the math completely changes.
Wait, so a spacecraft can launch from Earth with just enough fuel to break out of the atmosphere and reach the orbital depot?
Yes, and fill up the tank in space.
Oh, that is brilliant.
Which means the spacecraft departing Earth can be radically smaller and cheaper, or more likely, it can use that saved mass to carry vastly more actual cargo.
Because you aren't carrying all that extra fuel up the gravity well.
Exactly. You've completely broken the bottleneck of human expansion. Water off-world is literally the fuel for a self-sustaining ecosystem. It cuts the umbilical cord to Earth.
That completely flips the script. We aren't mining space to enrich Earth. We are mining space to escape Earth's gravity penalty. And once you break that bottleneck with fuel, I imagine the metals from the M-types and the silicates from the S-types become the next phase of the off-world economy.
They absolutely do.
But again, kept in space. We are talking about in-space manufacturing, taking those materials and building the infrastructure of the future in orbit, rather than trying to launch it all from Cape Canaveral.
That's the logical progression. But manufacturing microgravity isn't just a logistical convenience.
It's not.
No, it isn't just about building things without having to launch them. It's about building things that are physically impossible to build under the crushing weight of Earth's gravity.
Oh, right. Here's what fascinates me about this. You always assume gravity is just, normal, a constant.
Right, it's just the background of our lives.
But gravity actually ruins a lot of delicate chemistry in manufacturing.
It creates immense chaos at the molecular level. Down here on Earth, any manufacturing process that involves heating fluids or melting materials has to deal with gravity-driven convection.
Oh, the heat rising.
Exactly. We all know hot air rises and cold air sinks. But the same thing happens in molten glass or liquid metal. This constant churning, this thermal convection, creates microscopic flaws, bubbles, and structural weaknesses.
Because it won't just sit still.
Right. You also have sedimentation, where the heavier elements in a molten alloy naturally settle to the bottom before the mixture can cool.
Making it impossible to create perfectly uniform blends of certain metals.
Exactly. But when you remove the strong gravitational pull, materials behave in entirely new, pristine ways.
Like fiber optics, right. I was reading about Z-bland glass.
Oh, yes. Z-bland is a perfect example.
On Earth, when you try to make these ultra-high-performance fiber optic cables, gravity causes the glass to crystallize slightly as it cools, and those tiny crystals scatter the light, degrading the data signal over long distances.
That's the convection at work.
But in microgravity, without that convection...
Without convection, the molecular structure remains perfectly amorphous. The glass doesn't crystallize.
So it's perfectly clear.
Exactly. You can pull ultra-pure, flawless fiber optic cables that transmit data vastly better with orders of magnitude less signal loss than anything manufactured on Earth.
That's incredible.
And it's not just glass. You can grow perfect, massive silicon boules. Those are the giant crystals used for semiconductors and computer chips without any of the structural defects caused by gravity warping the crystalline lattice.
Wow.
You can mix advanced metal foams or exotic alloys where heavy and light metals stay perfectly suspended together instead of separating out like oil and water.
It is an entirely new industrial revolution waiting to happen, literally suspended in the vacuum of space.
It really is.
I mean, the materials derived from these asteroids could eventually support the orbital production of technologies we can barely conceptualize right now. Better batteries, flawless quantum computer components, massive solar reflectors.
Built from off-world materials.
And this seems like the massive looming but in all of this.
There's always a but.
Right. Finding an ice-rich or metal-rich asteroid is one thing. Understanding the theoretical chemistry is one thing. Actually getting the ice or the metal out of the rock in the freezing, irradiated vacuum of space is a completely different nightmare.
The nightmare is the appropriate term, truly.
Because it's just so alien.
Because the engineering in the void breaks almost every intuitive rule we rely on down here. It forces us to confront the intense physical challenges of microgravity mining, and honestly, our terrestrial instincts are almost completely useless.
We just take gravity for granted.
We do. Think about how mining works on Earth. It's incredibly difficult, yes, but we take massive physical advantages for granted. We have atmospheric pressure, we have friction, and most importantly, we have the Earth pulling everything down.
We have weight.
Weight, exactly.
Yeah.
If you want to drill into a granite rock face on Earth, you bring in a massive diesel machine, you push down on the drill bit, and gravity and friction help hold you and the machine firmly in place, and the drill bit bites into the rock.
The Earth basically pushes back.
Right. But in space...
In space, you don't have that leverage. You're dealing with basic Newtonian physics in a vacuum.
Equal and opposite reactions.
Right. If you float up to an asteroid, turn on your massive multi-million-dollar industrial drill, and push it against the surface of the rock, the drill doesn't penetrate the asteroid.
No, it does not.
The asteroid pushes the drill and the spacecraft attached to it violently away into deep space. You have no leverage.
None. Zero. Without gravity to anchor the machinery, traditional excavation methods involving applying downward torque are entirely useless.
So what happens?
Well, you spin a drill clockwise, the asteroid pushes back, and suddenly your entire spacecraft is spinning counterclockwise out of control.
Oh man, that's a disaster.
You have to somehow anchor your spacecraft or your mining apparatus to the object before you can apply any significant mechanical force.
Right, you have to strap yourself down.
But anchoring is incredibly dangerous because asteroids vary enormously in their structural integrity. We kind of think of them as solid monolithic rocks, like giant floating boulders of solid granite or iron.
And some are, right? Like the M-types.
Some are. But many of them, particularly the smaller S-type or C-type ones, are what planetary scientists call rubble piles.
That concept is deeply unsettling to me.
It's not a comforting term, is it?
No, a rubble pile is exactly what it sounds like. It's not a solid rock. It's a chaotic, floating collection of boulders, loose gravel, and dust that are only loosely held together by their own incredibly weak collective gravity.
Right.
They are basically floating debris fields pretending to be planets.
They are exceedingly fragile aggregates.
Huh.
If you try to land a heavy spacecraft on one or shoot a harpoon into it to anchor your mining equipment, The mechanical stress could be catastrophic.
Like breaking a window.
Exactly.
Yeah.
The asteroid might behave completely unpredictably. Because there is so much empty space between the loosely packed boulders, it might absorb the impact like a sponge, swallowing your anchoring mechanism without actually holding on to it.
It just sinks in.
Yes. Or worse, the kinetic energy of your operation might destabilize the object entirely, causing it to break apart or uncontrollably eject massive amounts of high-velocity debris into the surrounding space.
I was trying to picture what this would actually be like for an engineering team trying to design a machine to do this, and the best analogy I could come up with is this.
Okay, let's hear it.
Imagine you are blindfolded, and you are treading water in the middle of a swimming pool.
Okay.
Floating in front of you is a loose ball of gravel and dirt. Now, try to aggressively drill into that ball of gravel without pushing yourself backward in the water.
That's a great visual.
One wrong move, one push that is slightly too hard, and the whole ball just dissipates into a cloud of pebbles.
Yeah.
You've lost your target, your drill is spinning out of control, and you are surrounded by high-velocity shrapnel.
That captures the sheer instability of these bodies perfectly. And we know this isn't just theoretical modeling. The real-world findings from recent sample return missions have completely shattered our previous engineering assumptions.
Like what missions?
We'll look at NASA's OSIRIS-REx mission, or Japan's Hayabusa 2. When OSIRIS-REx went down to collect a tiny sample of regolith from the asteroid Bennu, the engineers anticipated it would tap a solid surface, grab some dust, and bounce off.
Like a high five.
Exactly, a quick touch and go. But the surface wasn't solid. The regolith had almost zero cohesion. When the spacecraft's collection arm made contact, it didn't hit a wall. It sank deep into the surface.
Wait, it just kept going?
It just kept going. The asteroid behaved almost like a fluid pit of plastic balls. The spacecraft just kept sinking. If the automated systems hadn't fired the thrusters to aggressively back away, the entire multi-million-dollar spacecraft could have been swallowed completely by the loose material.
That had to be an absolute panic moment in mission control.
I can't even imagine the stress.
You send a probe hundreds of millions of miles, and it almost gets eaten by a space swamp.
A space swamp, yes.
And it's not just the structural instability, it's the dust. Every time you touch one of these things, every time you fire a thruster nearby or try to scrape the surface, you generate dust.
The dust is a nightmare.
On Earth, dust is annoying, but it eventually settles because of gravity. In microgravity, dust and debris generated by excavation might drift unpredictably for weeks, months, or years. It forms this abrasive, electrostatically charged cloud that clings to everything.
And it's not soft dust. Lunar regolith and asteroid dust are incredibly sharp and jagged because there was no wind or water erosion in space to smooth the edges of the particles.
Oh, right. No wind to round them out.
It acts like microscopic sandpaper. This abrasive cloud can clog delicate moving parts, severely degrade the efficiency of solar panels, and destroy sensitive optical sensors. It's a profoundly hostile environment.
It's brutal for any machinery.
And that hostility fundamentally alters how we have to approach the labor of extraction. I mean, think about trying to put human beings in that environment.
Like actual human miners.
Right. The gravity on these near-Earth asteroids is so minimal that a human worker, enclosed in a bulky, pressurized extravehicular activity suit, trying to swing a geological hammer or manually move a piece of equipment, could easily generate enough upward force to overcome the asteroid's gravity.
Wait, you're saying they could literally leap off the asteroid?
Yes, they could achieve escape velocity with a strong jump.
That's terrifying.
You push off a little too hard with your boots while trying to pry a rock loose, and suddenly you are floating into the endless dark, and the asteroid is shrinking behind you.
That is pure nightmare fuel. You swing a pickaxe, the recoil pushes you back, and you just drift off into the void while your oxygen slowly ticks down.
It's a very real danger.
So human miners, like the roughnecks we see in the movies, are completely off the table. The safety protocols required for human laborers in that kind of environment. The tethers, redundant life support, massive radiation shielding would be astronomically expensive and incredibly restrictive.
They wouldn't be able to get any actual work done?
Which brings us to the automated vanguard. If we are going to mine the solar system, we clearly have to do it with robots.
It is an absolute, unavoidable necessity. Robotics and artificial intelligence are the only viable path forward for space extraction. Space is simply too hostile, too dangerous, and overwhelmingly too expensive for human laborers.
So we're talking about a fully automated setup.
Yes, we are looking at the necessary development of an entirely automated industrial network. We need systems that do not require pressurized habitats, do not need a constant supply of breathable oxygen or water, do not need to sleep, and crucially, do not demand a multi-billion-dollar return ticket back to Earth when their shift is over.
But we aren't just talking about a remote-controlled bulldozer where a guy with a joystick sits in a Houston control room, right?
No, definitely not.
Because of the speed of light. The time delay in communications across millions of miles of space makes direct, real-time remote control impossible.
The latency is too high.
Right. If a rock is about to crush your rover on an asteroid out past Mars, by the time the video feed reaches Earth and you send the command to dodge, 20 minutes have passed and your rover is already flattened.
Exactly. You need autonomous engineering.
Here's where it gets really interesting.
That latency is exactly why remote control is insufficient. You need machines that can think and react locally. And you don't just need one smart machine, you need swarm robotics.
Swarm robotics.
This is where the field is heading. Instead of sending one massive billion-dollar mining machine, which, as we discussed, could fail catastrophically from a single speck of jagged dust in a vital gear, or sink into a rubble pile, you send a swarm of thousands of smaller, cheaper, highly specialized autonomous robots.
Biomimicry. It's like an ant colony or a hive of bees.
Precisely the model. They operate collectively, they communicate with each other constantly via local networks. They use advanced machine learning algorithms to adapt to the unpredictable rubble pile physics in real time.
So they figure it out as they go.
Right. If they encounter a surface that is looser than expected, they communicate that data to the rest of the swarm to adjust their approach. And the beauty of swarm robotics is resilience through redundancy.
Because you can afford to lose a few.
Exactly. If 10 of these small robots get destroyed by a micrometeorite impact, or their motor seize up from dust, or they accidentally float away, the mission doesn't fail. The swarm simply recalibrates, redistributes the workload, and keeps working.
It is awe-inspiring to picture. You have a highly organized colony of metallic ants operating in the void.
It's quite a visual.
You have scout robots designed strictly for navigation and radar mapping, buzzing around the asteroid to find the highest concentrations of ice. You have extraction robots carefully, slowly skimming that ice off the surface to avoid kicking up debris.
You'd need specialized refinery robots, too.
Right. Refinery robots sitting slightly off in space, catching the ice, heating it, and processing it into hydrogen and oxygen. And you probably even have maintenance robots whose sole job is to fix the broken extraction robots.
A fully closed loop.
Try to picture this scene. A ghost town industrial revolution happening tens of millions of miles away, in absolute total silence because there is no air to carry the sound of the machinery, operated entirely by algorithms.
It is a stunning, almost eerie vision of the future. And it suggests a profound reality about human expansion. Human civilization will extend its reach through machine-mediated industry long before large permanent human populations actually move into space.
Oh, interesting. So the machines paved the way.
The timeline of colonization is inverted from historical models. We will send the automated vanguard to build the infrastructure first. Robots building robots.
Automated refineries processing fuel for autonomous transport vehicles.
Exactly. Constructing the habitats, stockpiling the life support resources, and establishing the supply chains over decades, so that when humans finally do arrive in deep space in large numbers, the ecosystem is already there waiting for them.
The frontier will have been tamed by algorithms.
That's right.
It makes complete logical sense. You don't build a city in the middle of a lethal desert by sending 1 million people first and hoping they figure out how to dig a well before they die of thirst.
You'd send the equipment first.
You send the machines to build the aqueducts, set up the solar grids, and establish the agriculture. But, and this is but all this incredible, pristine engineering logic crashes headfirst into a very messy human problem. Politics and ownership. When autonomous engineering becomes the primary driver of our economic expansion, and armies of corporate-owned robots are out there generating trillions of dollars of infrastructure and harvesting unimaginably valuable resources, who exactly owns the rock they are standing on?
This raises an important question, space law. This is where the pristine, math-driven world of engineering and physics collides violently with human politics, history, and economics.
It always does.
Because we are looking at the opening of a completely new frontier, and the rules governing it are currently a massive, unresolved gray area.
And a frontier that is shifting rapidly in terms of who the key players are. For the first few decades of the space age, space exploration was entirely dominated by massive, state-funded government agencies.
Right. It was the Apollo era. It was NASA and the Soviet space program.
But today, the geopolitics are shifting heavily toward private aerospace and exploration companies. Private entities, backed by venture capital, are now driving the launch systems, deploying the massive satellite networks, and drafting the future infrastructure plans.
But these private entities are operating under a legal framework that was written for a completely different era. They are bound by international treaties drafted when going to space was essentially a superpower flexing contest, not an economic endeavor.
Okay, so what's the actual law we're dealing with?
The foundational document here is the Outer Space Treaty of 1967, and its core tenet explicitly prohibits national sovereignty claims over celestial bodies. It legally established the concept of res communis in space.
Res communis?
Yes, meaning it belongs to all mankind. No country can fly to the moon or an asteroid, plant a flag in the regolith, and say, this territory is now ours.
Which makes sense in the context of 1967. The treaty was designed to prevent the Cold War from turning into a literal colonial land grab on the moon. They didn't want nuclear missile bases on the lunar surface.
Precisely.
But it was written long before serious commercial extraction by private companies using robotic swarms became technologically plausible. And this creates a massive legal and economic paradox for us today.
A profound paradox. Because on one hand, if you are a private space CEO and you are going to spend $20 billion developing an autonomous robotic swarm to navigate deep space and mine a C-type asteroid for water, you absolutely must know that the water legally belongs to your company once you extract it.
Of course. You need to know you'll get a return on that investment.
Exactly. If there's no clear legal framework guaranteeing ownership, private investment in space extraction is completely economically impossible. No bank, no board of directors is going to fund a multi-billion-dollar mission if international law suggests that once you extract the resources, anyone else can just pull up and claim a share of it because space belongs to everyone.
Exactly. Without property rights, the capital required to build this massive robotic vanguard simply won't materialize. But on the other side of the paradox, if we do establish legal frameworks that allow private companies to claim ownership of extraterrestrial resources, we risk creating unprecedented monopolies.
It's a huge risk.
We risk a future where a handful of early-moving megacorporations or heavily funded nations secure unequal access to the vast wealth of the solar system, effectively locking out developing nations and the rest of humanity from the off-world economy.
And we are already seeing the first moves in this geopolitical chess game. Certain nations are not waiting for a new global consensus.
Who's making moves?
The United States, for instance, passed the Commercial Space Launch Competitiveness Act, and Luxembourg passed a similar law regarding the exploration and use of space resources.
Okay, so domestic laws.
Yes. Both of these national legislative acts explicitly recognize the rights of their private citizens and companies to own, transport, and sell the resources they extract from celestial objects.
Which naturally leads to massive pushback from international legal scholars. I mean, I have to play devil's advocate here. How can a single country pass a domestic law granting property rights to something that an international treaty explicitly says no nation can own? Isn't that basically space piracy with better lawyers?
The lawyers would argue it is a necessary interpretation of a vague, outdated treaty.
I'm sure they would.
The proponents of these domestic laws rely on a very specific legal distinction. They argue there is a difference between claiming sovereignty over the asteroid itself, which is forbidden by the 1967 treaty, and claiming ownership of the resources extracted from it.
That feels like a thin line to walk.
They often compare it to maritime law on Earth. No nation owns the high seas, right? International waters are open to everyone. But if a private fishing vessel pulls a fish out of those international waters, the company owns the fish.
Ah, the space fish defense.
The space fish defense, exactly.
So you don't own the ocean, but you own what you catch. You don't own the asteroid, but you own the platinum you chip off it.
That is the argument. But critics argue that when your fish happens to be a trillion-dollar planetary core and extracting it alters the fundamental autonomy of Earth, the maritime analogy breaks down completely.
It's a little different than catching a tuna.
Just a bit.
Yeah.
We are looking at the dawn of an era that heavily resembles terrestrial maritime exploration, colonial expansion, and intense industrial resource competition.
Right.
But there is a crucial difference here that we must acknowledge, which shifts the ethical calculus. In terrestrial colonialism throughout history, empires fought brutally over finite resources, often displacing, exploiting, or destroying indigenous populations in the process.
Some of the darkest chapters of human history.
Exactly. But space introduces an entirely new scale. There are no indigenous populations on these asteroids. No one is being displaced. And the resources are effectively vast beyond current human consumption.
The bottleneck isn't scarcity. It isn't that there isn't enough platinum or iron or ice to go around. There's enough to build millions of orbital cities. The bottleneck is technological access.
Right.
It's about who has the rockets, the deep space telemetry, and the robotic swarms to get out there first.
That is the crux of the geopolitical tension. While the resources themselves are virtually infinite, the near-term economic advantages of being the first to harness them are staggering. It is undeniable that this legal battle isn't just about return on investment or corporate quarterly earnings. It's about what kind of species we're going to be as we step out into the dark.
That's a huge question.
Will this new frontier be managed cooperatively, with frameworks that try to distribute the benefits across humanity? Or will it be a hyper-competitive rush that simply replicates the inequalities and conflicts of Earth's history on a cosmic scale?
So what does this all mean? We've gone from the violent collisions of ancient protoplanets billions of years ago to the complexities of microgravity robotic swarms to international legal loopholes being debated right now. It brings us to a massive philosophical and existential crossroads.
It really does.
Because beneath all the economics and the space law, there is a very strong, very compelling environmental argument for doing this. Asteroid mining isn't just for billionaires wanting more metal.
For many scientists and futurists, asteroid mining is viewed not merely as an economic opportunity, but as an absolute ecological imperative.
Why is that?
Look at the state of our current biosphere. Right now, on Earth, maintaining our high-technology civilization requires incredibly destructive extraction practices. We are tearing up ancient, fragile habitats to get at veins of copper.
Right.
We are generating massive toxic waste lakes to refine rare earth elements. We are consuming enormous amounts of fossil fuels just to build the batteries, the electric vehicles, and the computer chips that we claim will save the environment.
We are effectively destroying the biosphere in an attempt to save the biosphere. The clean energy revolution requires incredibly dirty mining.
It does. But extraterrestrial mining could theoretically allow us to shift that destructive extraction off Earth entirely. Imagine a future where the heavy, toxic, resource-intensive industries are moved into the dead vacuum of space, where there are no ecosystems to pollute.
No groundwater to contaminate.
No endangered species to displace. We could turn Earth back into a garden, a zoned residential, cultural, and ecological preserve, while the dirty work of civilization happens millions of miles away in orbit, powered by limitless solar energy.
It's a beautiful vision. But the fear, and it's a very valid, deep-seated fear for many people, is that by doing this, we are just indefinitely extending extractive capitalism without addressing our core behavioral flaws.
The counter-argument, yes.
If we don't fix the underlying cultural mindset of infinite consumption and waste, taking our industry to space just kicks the can down the road. It risks reproducing the same exploitative systems, the same disregard for our environment, just on a much grander solar system-wide scale. The argument is that we aren't actually solving our problems. We are just exporting our worst habits to the asteroid belt.
That tension is the core of the philosophical debate, and it involves a profound psychological shift for humanity. Think about our relationship with the cosmos.
Okay.
For millennia, for the entirety of human existence, space was a realm of mythology. It was the ultimate realm of transcendence, distance, and mystery. The stars and the wandering planets were things we worshipped as gods, or navigated our ships by, or simply looked up at in awe. Now we're standing on the precipice of integrating those celestial bodies into mundane human economics.
We are looking at the night sky and seeing a quarry. We are looking at a glowing point of light and seeing a gas station. That is a heavy, tangible loss of wonder. But I think you have to weigh the cost of losing the mystery of the night sky against the guarantee of humanity's long-term survival. Because when you strip away the romance, the existential stakes here could not possibly be higher.
Existential stakes are absolute. The Earth is incredibly resilient, but human civilization is vulnerable. We face accelerating climate change, severe resource depletion, fragile supply chains, global pandemics, and, ironically, the ever-present threat of asteroid impacts themselves.
Right.
As long as all of human history, all of our art, all of our culture, and all of our potential is confined to a single fragile biosphere at the bottom of a gravity well, we're at risk of extinction. A single catastrophic event could end the human story forever.
All our eggs are in one basket?
Expanding our industrial and economic activity beyond Earth, utilizing these vast asteroid resources, is how we build a multiplanetary industrial base. It reduces our dependence on a single planet's ecosystem. It provides the material wealth and the energy to expand our presence across the solar system. It is arguably a necessary evolutionary step if our civilization is to survive deep into the future.
It really is this strange, almost poetic convergence of cosmic time and modern industrial civilization.
How so?
We are talking about resources that were forged in ancient supernovas, dying stars that exploded before our sun even existed. Those heavy elements drifted through the nebula, gathered into primordial protoplanets during the chaotic birth of our solar system, were violently shattered by cataclysmic impacts, and have been perfectly preserved in the freezing, silent vacuum for 4.5 billion years.
Wow.
And now, today, they're about to become the silicon in our computer chips. They're about to become the liquid oxygen in our orbital fuel depots and the structural steel of our deep space habitats.
It transforms deep-time geological relics into the very components of human technological survival. The solar system is shifting right before our eyes. It is changing from a distant, mysterious place we visit occasionally with fragile, expensive scientific probes into an integrated economic and industrial domain. We are transitioning from a terrestrial species completely confined to the surface of Earth into a technological presence capable of operating across the larger architecture of the solar system.
It is an incredible journey we've mapped out today. We started by realizing that these drifting rocks aren't just space rubble. They are the ancient, shattered cores of dead protoplanets floating in the dark.
The cosmic yolks.
Right. We looked at how the absolute tyranny of Earth's gravity well makes water simple, frozen ice the most valuable and revolutionary resource out there, acting as the ultimate fuel that will break open our expansion into the solar system.
The Hydrolux gas stations.
We explored the terrifying, non-intuitive physics of microgravity engineering, where a single wrong drill push can send you spinning into the void, which makes autonomous, robotic swarms the mandatory vanguard of our expansion. And we wrestled with the immense legal, geopolitical, and existential battles that will define who we become as we step out into this new, infinite frontier.
It is a transition that requires us to rethink everything. From the fundamental physics of how we build machines, to the legal frameworks of how we share wealth, to our ultimate place in the universe.
And I want to leave you with a thought that builds on something we discussed earlier about those M-type metallic asteroids. We talked about how they are the exposed cores of ancient protoplanets' worlds that tried to form billions of years ago but were violently shattered in the chaos of the early solar system.
Yes.
Think about what we are actually proposing to do. If we successfully harvest these dense metallic cores and we use those metals to manufacture our massive deep space vessels in orbital shipyards, we aren't just building ships out of raw materials.
No, we aren't.
We are taking the primordial remnants of dead, shattered worlds, and we are giving them a new purpose. We are effectively reanimating the corpses of dead planets. We are turning the ancient ghosts of the early solar system into the very vehicles that will finally carry humanity to the stars.
That is a profoundly beautiful way to look at the future of our species.
It really makes you look up at the night sky a little differently tonight. Thank you for taking this journey with us. Keep looking up, and we'll catch you on the next one.